Assalamu alaikum students. Today's topic is going to be about young double slit experiment. Now, first of all, we have to understand what is interference, due to which we have to understand the young double slit experiment. The condition to observe the interference of light. Now, what is interference? So first of all, we have to understand. The interference is described as the effect produced by the superposition, or in simple words, you can say overlapping of waves, or light waves, you can say, of waves from two coherent sources. What does coherent means? Of the same wavelength. So the wavelength should be the same, passing through the same region. Now in this condition, interference is formed. Now let us see the conditions in the of the interference of light. The following conditions are required for interference of light waves. Number one, the light wave must come from the two coherent sources. That means the source which is sending out the light should have the same wavelength. The amplitude of the wavelength or the wave must be equal or nearly equal. That means the maximum distance from the mean position of this wavelength or the two wavelength should be same. Point number three, the light wave should be perfectly monochromatic. Monochromatic. Mono means one, chromatic means color. One color, the wavelength should be of one color. Either it should be of red color or blue color. The red color has a wavelength of 750 nanometers. So the other source should also have the same wavelength of 750 nanometers. Now, this is a much larger wavelength. Question number 4, the path difference of the wave from two sources must be small. That means if one wave is traveling over here, then the path difference of the other wave should be very much smaller than the other. That means the distance between the two waves should be very smaller if they are traveling. The principle of linear superposition should be applicable. That means that if one wave is traveling in this line, the other wave should also travel in this line in order to interfere. Otherwise, what will happen? The two waves won't interfere in either cases. So they should be in a linear position so that they can interfere with each other. So these are the conditions of interference of light. On the basis of these, the Young did experiment on these lights and form an experiment. In 1801, Thomas Young performed his famous double slit experiment, which provided experimental evidence in the favor of wave theory, which proved that light was wave. These evidence basically prove that light was wave, which was later on confirmed that light has duality. It is as perform as a wave as well as particle. About the nature of that light, the principle of this experiment is based on the division of wavefront, or you can say wavelength. That means the wave were divided into two parts. To get the phase coherent, that means the same wavelength between the two interfering lights or sources, the Young used a trick. What trick was that? He used the same source. The source was same, because if he thought that if the source is same, the light coming out of it will also have the same wavelength. And when he split those light, or that light split the wavefront of the same monochromatic light into two parts, then allowed to interfere. That means if he allowed this light coming from the source, he split them by using two slits, let's call that A and B, and then allowed that light to interfere with each other. Then when we can basically see now that the light basically produces fringes. One is dark and one is bright. Why? Because now the light is monochromatic. Only two conditions will be formed. Either it will be a constructive or destructive interference. In the case of constructive interference, the light will be bright. while in the case of destructive interference, the dark fringe will be formed. Now let us understand the experimental arrangement which he took. Now the experiment arrangement of Young double slit experiment is shown in figure. Now as we can see, in this case, the monochromatic light from the source through the narrow vertical slit C falls on the other two narrow slit A and B. Here is the source, and light comes from here from point C and enters into these two slits A and B. And as we know, because the wavelength coming out of these sources is same, the wavelength coming out of these slits should also be the same. So if we form an interference over here of these two wavelengths, then these interference can be shown on the screen as well. The slit A and B are very close to together and parallel to C. That means if C is in this direction, A and B is also in the same direction. The slit A and B acts as the two coherent sources. Now A, as you can see over here, now as you can see, A and B are now two sources which are producing the same wavelength. This a screen is placed at a certain distance L beyond the slit A and B. Now the screen, which is shown by the yellow color, is at a distance L from the two slits. Now, as we have understood this construction of the experiment, let's see what happens in this whole case. What is the scenario? The interference of light wave in the Young's double slit experiment can be explained by using Huygens principle. Now, in that case, the slit C sends out a circular wavefront, and since the distance of the slit A and B from the slit C are the same, so the same wavefront arrives at A and B. Now, in this case, we will understand through animation that how the wavefront basically of one wave travel and pass on to the second slit, the secondary slit, as you can say over here, from C to A and B respectively. The point of wavefront A and B then emit the wavelets in the phase which interface basically with each other. And hence the wavelet emerging from slit A and B are coherent, having the same frequency and amplitude. This method of obtaining the two coherent sources of wave is known as division of wavefront. Now, this is a situation what is being explained in this whole paragraph. The waves are emitted out from point C, as you can see over here, as they have the wavefront reaching up to point A and B, which have the same frequency, same uh, you can say wavelength and phase. So they will also emit the same phase like this. To basically mention the difference of the two slits, I've mentioned one with red color and one with blue color. Although they have the same wavelength, but over here, for the better understanding, I have mentioned them with different colors so that you can see the interference between them. So as they move in constructive and destructive interference toward the screen, as you can see over here, they interfere like this at certain points. And due to this interference, dark and bright fringes will begin to appear on the screen, right over here. This is the screen, and dark and bright fringes will begin to appear over here. Now, if you want to see that light coming from here, light coming from here, basically interfere with each other at different point on the screen, as the slit A and B are narrow, that means this part is very small, enough so that the diffraction causes the emerging beam of light to spread into region beyond the slit. That means they are allowed to spread or scatter beyond the slits, and they basically interfere with each other. The superposition of wave from slit A and B produces interference. The constructive interference occurs along the solid line and bright fringes observed on the screen. Because of this line, constructive interference basically occurs. The point at which the two uh, trough crusts basically interfere with each other, there we can see the constructive interference and bright fringe will be formed, whereas destructive interference occurs along the broken lines and dark fringes are seen on the screen as shown in figure. Because of this reason, we can see bright and dark fringes over here. Over here we can see there is a bright fringe, and over here we can see as a dark fringe. So in this case, we can say now to discuss the experimental quantity and get expression for the separation of the two successive bright or dark fringe, let us consider the figure. Now in this case, we can say the distance between A and B is D. Here D is the separation between the slit A and B. L is the distance of the slit from the screen O, and here is the distance from the slit to the screen, which is represented by L, and this is the point O, which is the center of the screen, and O the center point of the screen. Now here is the labeling of the whole diagram. The distance between the two slits is A, the distance from the slits to the screen is L, and the center point is known as O. Now, if we can see over here, if the construction is basically in the center point, if we see that a red light basically, or a light coming from here, from A point, and a similar light coming from here from the B point, over here it will always be a constructive interference at point O. Why is this so? Because the path distance from point A and from end point B is basically the same. Now this is the reason we have understood that at point O there will be always a constructive interference. Now if we move it to another point, let's call it point P. Now at this point the distance from point A, as you can see from here, and point B is different. The path difference has occurred now. This path difference will cause either constructive or destructive scenarios. Now in this case it is a constructive interference, because at this point we can see a bright fringe of yellow color, we can say. Now if we want to understand what is happening, where do the constructive interference will occur, or how it will occur, or how can we calculate how should it occur, we have to understand this procedure. The path difference between the waves reaching point O and A is zero. That means this point and this point, when they both occur at the same time at the center point, they will always make a constructive interference because the path difference is zero. So they arrive in the same phase and constructive interference take place at point zero. Hence, bright fringe is observed. That means at this point, always bright fringe due to these difference of uh, basically no difference between the path difference occurs at this point. So that is why there will be a constructive interference in this case. But if we consider another point, let's say P, the wave traveling from slit B to point P on the screen covers a distance S extra. That means this much part of P, let's say, is S, and this much part is covering extra to cover the distance from point B to point A as compared to point A. Now it says that far as than for the from the slit A. Applying the condition, the constructive interference, the point P will be bright region if the path difference S has an integral multiple of lambda. That means if the whole distance from here till here, this point, the extra distance covered by B, if it is equal to a whole lambda or any multiple of lambda, then at this point the wave reaching at this P point will also be the same wavelength, and we can see a constructive interference acting over here. But if this much region does not basically follow the same path length or wavelength lambda or half of wavelength in this our case, then it will be destructive interference, which we'll discuss later on. Now he says if the path difference BP, that means extra distance from BP, V minus AP, which is the distance S, this is distance S right over here, is 0 lambda, 1 lambda, 2 lambda, any multiple of lambda, then we can say then it will follow a constructive interference. So this is the angle. This is the point which is the main point of this Young double slit experiment. That means this much distance, if it is equal to lambda, which is equal to S actually, if it is equal to lambda, then we can say that at this point P there will be constructive interference. But if this is not a full lambda, or you can say a whole lambda, then there will be a destructive interference at the end. This is the concept of Young double slit experiment. So if he says that BQ is a whole lambda, any multiple of lambda, it can be 1, 2, 3, saying m, where m is a variable having the value of 0 plus minus 1 plus minus 2 plus minus 3 and so on. But if it is a whole number, then there is a whole lambda, and at the end of this wavelength we will see a bright fringe, and BQ is equal to S, and it will be equal to d sine theta. Now if we compare equation 1 and equation 2, but first of all, let me explain how does this equal to d sine theta. So here is the triangular form. So here's point A, this is point B, this is let's say point Q, and this is theta. This is D, the distance between point A and B, and this is S. As we know from the concept of trigonometry, sine theta is equal to perpendicular over base, or you can say, sorry, not perpendicular over base, perpendicular over hypotenuse, perpendicular over hypotenuse, or we can say adjacent over hypotenuse. Now what is perpendicular over here? S is perpendicular over here, and what is the hypotenuse? D is the hypotenuse. So S, we can say, in other words, S can be represented as d sine theta. So from here we can say BQ or S is equal to d sine theta. Let us remove this one and continue with our derivation. Now let us compare these two equations. Let's say equation number 1 is this one, and equation number 2 is this one. So both of them are equal to S. So d sine theta is equal to m lambda. So here it is, d sine theta is equal to m lambda. This is the concept for the bright fringe. Whenever the lambda is a whole number, we'll get a bright fringe. For the center point O, we have m is equal to 0, and a bright fringe is observed, which we have already discussed in this case, called zero fringe. From m plus 1 or minus 1, the first order will be maximum and will be above and below the center point O bright fringe. That means that on the top side, that means first fringe and bottom fringe, both are 1. They both have a bright fringe after the dark fringe, which is half actually. Whenever there is a half lambda, there is a dark fringe. Whenever there is a whole lambda, we can say there is a bright fringe, simply putting it. So here is the condition. We have the triangular form of formula. This is theta, this is D, this is point A, this is point B, and this is point Q. This is S, and we are using the formula of trigonometry. S sine theta is equal to S over D. That means perpendicular over hypotenuse. S will be equal to D sine theta, And if this d sine theta is equal to a whole lambda, which is over here, then it will be d sine theta is equal to m lambda, and we will see a constructive interference at point P. Now for the destructive interference. In the destructive interference, almost everything remains the same, but as you can see at this point now, it is a bright fringe, but in destructive interference at this point, if this much distance, which is s, is equal to any multiple of lambda or half, basically half a lambda, then over here there will be a dark fringe. On the other hand, if path difference s between the two wave of A and B, P is an odd integral multiple of half a wavelength, then the two wave will be 180 radian or pi radian out of phase. So destructive interference will take place and dark fringe will be observed. So if in this case, let's say the wave is going over here like this, and over here half wavelength is over here, and as you can see there is a phase difference of 180-degree over here. So what will happen in this case? There will be a destructive interference. As you can see, the colors have changed as the phase difference has occurred. The phase difference is 180-degree, so there will be a dark fringe over here. That means there is destructive interference happening at this point. So it is all because of this S, the distance between B and Q. So let us derive its formula. So we have the same concept, A, P, and Q of the triangle. This is angle theta. This is S, and this is D. Sine theta is equal to S over D. S will be equal to D sine theta. But if this D sine theta is equal to half a lambda or any integral of half a lambda, you can say, then it will be a destructive interference. And this is what is being mentioned over here. D sine theta is equal to half a lambda, or you can say 3/2 lambda, which is 1.5, 5 lambda by 2, or you can say 2.5 lambda. Any half lambda which is formed, then at the end point at point P, we'll see a destructive interference. So, or we can say in the simple generalized manner, D sine theta is equal to m plus 1 plus half a lambda. That means into half a lambda. So the answer will be, whenever we get the answer, it will be a destructive interference if the lambda is half in this region, which is S right over here. Now, position of the fringe. If we want to calculate what is the distance from where it is bright, where it is dark, this distance basically is represented by y. And how can we calculate that much distance? So here the distance from point O, which is the center point, to point P, at which constructive or destructive interference may happen, y distance is taken. That we take the distance that much is equal to y. Now, to locate the position of nth order, any order you can say, bright or dark fringe on the screen, we have to find expression for its vertical distance y from the center point O, which is represented right over here. We have to find this much distance, that which order of wavelength which we are taking over here. So if we basically make a triangular form over here from point P to point E, which is the shown by a dashed line or dotted line, we can make it into a triangular form. We can solve it by a similar triangular concept. Let's see over here. If I imagine a triangle form of this PEQ, oh sorry, PEO, sorry, this triangle, and this similar triangle as ABQ, then we can solve the answer for y. So let us make a solid triangle over here. So to do so, consider two triangles ABQ and PEO are similar right angle triangles, as we can see over here. Let me mention the one triangle over here. So this is a triangle PEO, And let me draw the other triangle, which is ABQ, which is right over here. So this ABQ and PEQ, both triangles are similar to each other. Now, this much distance from the center point E to point P, if we move it closer to the center point, that much distance will be equal to L. That means the distance from here to here will be almost equal to L, as you can see from the movement of this dotted line. It will be almost equal to L if the theta is very, very small. Now, if we compare these two triangles, triangle ABQ and triangle PEO, side by side, we will be able to see that how they are similar to each other. Let us move it apart, rotate it. Now they are opposite to each other. Let us swirl it around and see that if this triangle is of the same shape of this triangle. So if we rotate this triangle by 180 degree, as you can see, we are rotating the triangle over here. If we rotate like this, as you can see, the shape of this triangle is same, and we move it back again. So it means that these triangles are similar to each other. Now, let us mention the parts on it so that we remember the parts which are given on the triangle, which we have taken from here. So let us move the part A, B, and Q from this point and mention it over here. So this is the same triangle over here, and now we are comparing this triangle PEO and this triangle ABQ. Now, as we can see, this is the perpendicular part, which is S. Over here, the perpendicular part is Y. Here, the hypotenuse is basically D. And hypotenuse, as we can say, the hypotenuse is almost equal to L because it is very, very small, or theta is very, very small, we can say in this case. So in actual, the y is very, very smaller than L, and PE is almost equal to EQ. That means this much distance is almost equal to this much distance, or we can say when this point P is very close to point O, in that case, PE is almost almost equal to EQ, which is the distance of L, as mentioned over here. And so the above equation will become, so if we can see over here, S, which is the perpendicular part over the perpendicular part of the other one, and D, which is the hypotenuse of a triangle A, B, and Q, divided by L, which is the hypotenuse, or you can say part of the triangle PEO. Now, if we want to find out why, we should rearrange the whole equation over here. So we can find out the value of y. Y will be equal to L into S divided by D. And in this way, we are able to find any distance, nth distance of the fringe occurring on the screen. This is the formula. Now for dark fringe, mth dark fringe. To locate the mth dark fringe, putting the values of S of the distributive interference, we have any lambda, which is of half. As you can see, Y dark is equal to L lambda divided by 2, or 3L lambda divided by 2. So it is half in each case. So if it is half in each case, we will find the Y value, or the distance from the center point to any dark value, by putting the value of lambda by 2 in this formula. So this is the generalized formula of Y dark and mth value of dark value of wavelength occurring at the screen. It will be equal to m plus half into L lambda divided by T. Now, what is the distance between two consecutive bright fringe and two consecutive dark fringe? So let us assume the first bright fringe. So the distance between two consecutive means one regularly after the other, just after the other. Like one is bright over here, the next after bright after this one is this one. So this is the first one, and this is the second one. So 1 and 2 are the two consecutive bright fringe in this case, or the dark fringe is known as fringe spacing. So this thing is known as fringe spacing. In case of bright fringe, the fringe spaces between first order and second order, which is over here. This is the first order fringe, and this is the second order fringe. So let us put the values from the previous equation. It will be 2 L lambda divided by D minus L lambda divided by D. Now, if we subtract them two, we'll get the value of L lambda divided by D. That means the difference between them two is going to be a lambda, because L over D is a constant value. It doesn't change throughout the experiment. So lambda will basically be the difference between the two fringes. If we consider the dark fringe, now if this is the half of fringe and this is 1.5 or 3 by 2, we can say, then what is the uh, difference between these two fringes? The fringe spacing between lambda first and second order fringe, dark fringe, it is going to be 3 by 2 L lambda divided by T minus L lambda by 2. That means 1.5, we can say in other words 1.5 L lambda divided by D minus zero point 0.5 L lambda divided by D. So if we subtract these two, we'll get basically taking common L lambda divided by D, we get 1.5. We can write down it clearly. So it will be 1.5 minus 0.5, and we have taken common L lambda divided by D. So if we cancel this out, it will get 1 L lambda divided by D. So it will be also a whole lambda in this case. So the fringe spacing in this case will be equal to L into lambda divided by D. So this was the topic of Young double slit experiment. I hope you enjoyed this topic, because I certainly did. Inshallah, we'll meet again with a new topic. Until then, take care of yourselves. Allah Hafiz and bye-bye.